Hello students, good afternoon. Let me start the ITC class. In the morning class, I was telling that most probably I will come. Now, with full probability, I have come to the fifth hour. I was telling in the morning that if any emergencies happen, sometimes the probability of taking the classes may also be changed. But now, as I have taken this fifth hour class, that means the information content of me taking the fifth hour class is actually lesser because it is as per the timetable. Okay. So the fun apart, let me start the class now. I had mentioned something about entropy earlier, and I had told that the entropy which we use in the mechanical engineering term is different than the term which we use here now. Many times in English, what happens is the word is used at many places with the different meanings. Even though the word is the same, it is used in different occasions with the different situations with the different meanings. So here the meaning of entropy means it is related to the information theory. It is about the net information content. So now let us discuss about what is the meaning of entropy. Information source emits the messages and the communication system transmits each message as a sequence of symbols. This you already know. However, the information content is not uniform because of the following. The meaning of this wording, information content is not uniform, which means we are basically dealing with discrete information sources. And in addition, we want to have variable length coding. We don't want to have a fixed length coding, because if the fixed length coding is used, then unnecessarily we are going to send a lot of data. So when we have a variable length coding, naturally the information content is non-uniform as such. And there are other reasons why the information content is not uniform. Let us see that one by one. First one is there is randomness involved in the symbol selection, which means when you type a message in your mobile phone, let us say using a WhatsApp app itself, now only you know what you are going to type, and whatever you are going to type at that particular instant, you are going to decide upon the wordings which we are going to use. So actually whatever you are going to type out is dependent on that particular situation, and the words which you type is not predefined. That means there is randomness involved in the symbol selection. In general, in nature, it is randomness as well as planning, both are there together. For example, in a jackfruit tree, there are so many flowers, and the jackfruit is coming out of the jackfruit tree's body itself. And the jackfruit as such, is it random or is it planned? If we have to say, it is wonderfully planned inside with so many seeds and so many fruits inside. And jackfruit's outside is also completely covered with the thorns. We should say that it is completely planned. But in the jackfruit tree, on the body of the jackfruit tree, at which part it is going to have a bud and it is going to have a fruit, that we don't know. That is random. This way in nature, there is randomness everywhere. At the same time, there is planning also everywhere. So we should say nature is randomly planned or planning is done randomly. both are applicable that way. So there is randomness involved in the symbol selection. Why? Because our communication sources as such are dealing with the natural information, and there is randomness. To elaborate this further, let us say I am going to write a book. When I am going to write a book, I don't only have a concept there. For which concept I have to write a book, that concept will be there. The real sentences will come out only when I start typing the book. If I start typing using the computer, only when I really start typing the book, all the conceptual knowledge will be transferred into an English sentence. And in the English sentence, which are all the wordings I am going to type out at that time is not actually fully predefined, which means concept is planned, whereas its outcome, in the outcome, whenever it is going to be an information, there is randomness involved. So based on that, whichever wordings I am going to type out, in whichever way I am going to frame the sentences, all those things, there is randomness. This is the first thing. Second thing is, the symbols are statistically dependent. This is a very important point. The symbols are statistically dependent, which means what? In English language, when we type any sentence, all these 26 alphabets, they are not actually independent. They are statistically dependent. Even though A to Z, they are individually separate alphabets. When we make words out of these 26 alphabets and when we make sentences out of these 26 alphabets, there is dependency between vowels and consonants. And there is dependency in between word to the next word. The first word and the next word, they are statistically dependent. For example, this particular sentence itself, the symbols are statistically dependent. In this sentence itself, this the is there, symbols is there, are is there, which means those symbols, they are related. Symbols are, they are related. Symbols are statistically, they are related. The symbols are statistically dependent. There are only 5 words in this sentence, but all these 5 words are dependent on each other. Because the whole sentence becomes meaningful only when these 5 words are related to each other. Otherwise, unrelated wording will not have any meaning as such. Just like this, even in information, all the symbols which you use are statistically dependent because information itself is related to each other. Okay. Now, based on these two things, because of these two things, there is randomness involved in the symbol selection, and even the symbols are statistically dependent. Because of these two things, the information content cannot be uniform, and it need not be uniform. I had given you an example of this 64 kbps voice channel. There, if every speech sample is converted into 8 bits with the Nyquist sampling rate, it's a uniform data rate, that is 64 kilobits per second. That is applicable to the landline communication. But in case of the mobile communication or in case of the wireless communication, we want to conserve the bandwidth. We want to use the channel for maximum efficiency, and we are using a shared channel. In case of landline phone, it is not a shared channel. It is a individual channel for everybody. Maybe let us say, for example, if I take my landline connection to home and if I have a broadband connection to home, I will be using a copper wire cable from my home till the telephone exchange. It is not a shared channel. It is a dedicated channel for me. Whereas in case of a mobile phone, it is not a dedicated channel. It is a shared channel. The free space or the air medium itself is shared among everybody. So in such case, we want to send information, transmit information effectively. And at the same time, we want to conserve the bandwidth as well. Otherwise, there can be more and more of interference, noise, distortion. All those issues are there which we had discussed earlier. So in order to have an effective communication, it is better that we conserve the bandwidth or reduce the data rate. So we need not go for a uniform data rate where unnecessarily we end up sending more number of bits. Wherever it is possible to save the number of bits, we can save it because our information is dependent on the probability. Whichever is highly probable, which will have a lesser information, whichever is less probable will have a larger amount of information. This is one thing. Second thing is, whichever is alphabet from A to Z, whichever alphabet is occurring regularly, for that we can have a reduced number of bits. Whichever is not occurring regularly, for that we can have a larger number of bits. We need not have a uniform number of bits for all the 26 alphabets. Now, based on all these things, we can reduce the number of bits which we are going to transmit. I had told you one sentence earlier that we have to convey more, but we have to transmit less. By transmitting less number of bits, we have to convey larger amount of information. That is possible by means of all these properties of information. So, the information content need not be uniform at all. Information content can be non-uniform, and it is okay as far as the wireless communication channel is concerned, or even in the wired communication channel when multiplexing is happening, even the data rate can be non-uniform. Data rate need not be always uniform. That is the idea here. I will give an example. In between, if you have any questions, you can always ask. You can simply put one question mark in the chat box, and I will tell you to unmute yourself, and if you want to orally ask me also, you can ask. Let me give an example. In an English word, you appearing after Q carries less information than you appearing after T. For example, QU means it can be quick also, it can be Q also. Whereas TU can be Q stay, tumbler, cube, tulip, tune, turn, and so on. Which means U appearing after T is more probable. U appearing after Q is less probable. Which means for this U appearing after T, because it is more probable, we can have less number of bits because it is regularly occurring, where we save the number of bits. If U appearing after Q, which is less probable, we can have more number of bits because it is not occurring regularly. So in this manner, we can allocate the code for each word. This word is nothing but a collection of symbols now, and we can allocate different types of digital codes, binary codes for all this information, and because of which our information content need not be uniform, it will be non-uniform. Similarly, letter E occurring is more frequent than the letter Q occurring. So if at all we have to use a bit for a single alphabet, E can have lesser number of bits, Q can have larger number of bits. That way we save the number of bits. Okay. Now based on this example, let me elaborate a little further. Let the source emit m possible symbols with the probabilities of occurrence P1, P2 up to Pm. You can imagine this English language itself. English language contains 26 symbols. Now, let us generally take it as capital M. Let the source emit m possible symbols with the probabilities of occurrence of P1, P2 till Pm respectively. If the long message contains, let us say, n symbols, this capital N is the number of symbols, then the total information content of the message is given by this formula. I will slightly explain this further. English language contains 26 alphabets. So let this M be that 26. Now using English language, we write a big sentence. That big sentence will contain N symbols now. For example, let me count the number of alphabets here itself. If is containing 2, then space, D is containing 3, then space, then long is containing 4, then space, then message is containing 7, then space, then contains is containing 3 plus 3 plus 2, 8. So, N, then space, symbols is again 7. So, if at all I come till this N symbols, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 plus 4, 16 plus 3, 19, 20, 23, 26, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 44, 45 plus 3, 48, 49 plus 5, 54, 55 plus 4, 59, 60, 63, 66, 67, 68, 69, 70, then here space 71 plus 3, 74, 75, 75 plus 5, 80, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95. So till this comma, from this if till this comma, there are 95 symbols. Now these 95 symbols comprise of those 26 symbols of English language, 26 alphabets of English language. That is the meaning here. Now m possible symbols means the number of symbols which are available in the character set. Here n symbols means which is contained in the long message. Now in this example, in this particular sentence, we have 95 symbols. Now for that particular long message or this particular long sentence, what is the total information content? That can be defined this way: summation of I equals 1 to m. Why? Because we use only 26 alphabets. Now n into pi, n is the number of symbols in this sentence, and pi is the probability of each symbol. A will have a different probability, B will have a different probability. That way we go on till Z, it will have a different probability, which means n is the number of total symbols in the given message. In our example, this is this particular sentence. Pi is the probability of each symbol. And we already know what is the definition of self-information. Self-information is Lg of 1 over Pi. A's self-information is Lg of 1 over Pi of A. B's self-information is Lg of 1 over Pi of B. That way, this Lg of 1 over Pi is self-information, which means each character in the character set has its own information based on its probability, that we have seen in the morning's class. Now this is I of m and this is I total for the complete sentence. Naturally we have a summation of 26 alphabets because we have totally only 26 alphabets. Now even though we have 26 alphabets, sentence contains 95 alphabets or 95 symbols. Each symbol has a probability. So this is how we define the total amount of information. Summation of I equals 1 to m, n into pi into Lg of 1 over pi, and the unit is bits. Why the unit is bits? Because we are using log to the base 2 only here. So naturally here it will be bits only. Okay. Here we have assumed that the long message contains all the m symbols. That is important. We have assumed that the long sentence contains all the symbols. Now this particular sentence contains 95 symbols, and we have assumed that out of these 95 symbols, all the 26 symbols are present. Even though they may not be present here in this case, we have to assume this way, because in the real communication, it will not be just 95 symbols. It can be 95,000 symbols in a information packet. Later on, you are going to study more about routing and switching. Anyhow, we have a center of excellence in our department. Gradually, we will be learning routing and switching. In this routing and switching, you are going to learn more about how information is transmitted by means of packets. There is something called packet switching. So when the packets are moving from one source to the other destination, the packets contain thousands of bits, not just a few number of bits. So here, even though in this example I am telling you that n is only 95, in the real scenario it will not be just 95. It will be in hundreds and thousands. So in such case, there is a equal probability that all the 26 alphabets in the sentence are going to be utilized. For example, if you are reading a textbook, there is a complete probability that out of the 26 alphabets in the English language, all the alphabets are there present in the textbook, but with different probability. Same way here in the information theory. So we have assumed that the long message contains all the m symbols in multiple of times, and it is also assumed that the symbols are independent. A is statistically independent with B. B is statistically independent with C. That is how we have to assume, because the symbols as such are not dependent. For example, 1 is not dependent on 2, 2 is not dependent on 3, 3 is not dependent on 4. Okay, and 1 is not dependent on 0 also. But if at all you write 10,000 rupees Now 10,000 rupees, 10 followed by a comma, then 3 zeros. That is highly meaningful now. 10,000 rupees, 1 lakh rupees is still more meaningful. 10 lakhs is still more meaningful. 1 crore is still more meaningful. Okay, but the thing is that 1 and 0 are not related. 1 and 0 are statistically dependent. But when you write them as a single sentence or as a single set of information, they become dependent there, because we define meanings for the words. We define meanings for the numbers. Otherwise, alphabets as such are not dependent on each other. A is not dependent on Z, P is not dependent on Q. But when we write a word called ELEPHANT, let us say we write a word called elephant, then elephant word has a meaning. Even though E and L are unrelated, when I write them as ELEPHANT, they become related. We make them related. Similarly, 10000, they are unrelated. But when we say it is 10,000 rupees, they become related. So, we assume that the long message contains all the symbols and in multiple number of times. Naturally, if the sentence is containing 95 alphabets, many alphabets will come again and again. For example, you can see this T. T has come here. T has come here in contains. And T has come here in then. T has come here in the. T has come here in total twice. In content it has come twice. In the it has come once. Like that it goes on. Similarly, other alphabets, A has come many times, O has come many times, G has come many times. So naturally, these symbols have to come multiple number of times. And it's also assumed that the symbols are independent. That is, N is much larger than M. And we assume that the source is memoryless. What is the meaning of this sentence, source is memoryless? Source is memoryless means A and B are unrelated. Which means after a symbol is transmitted, the next symbol which is being transmitted is not related to the previous symbol. That way the source is memoryless. Now based on these assumptions, the total information content is given by I total equals N. Now this N can be taken out from this. This N is a very large number, so N can be taken out from this. So when the N is taken out, N comes out summation of I equals 1 to capital M, Pi, that Pi is the probability of each symbol, and Lg of 1 over Pi. Why did we take N out? We took N out because symbols are independent, source is memoryless. This way we make our life simple. This way we make our information theory course also slightly simple. Otherwise, if we assume that A is related to B, B is related to C, then life becomes more complicated. You know why? We will have to establish relation between A to B, A to C, A to D, A to E, A to F, A to Z. Again, we have to establish relation between B to A, B to C, B to D, B to E. Think about it. It is 26 to the power of 26. Those many relationships we will have. If at all we assume that symbols are statistically dependent, and if at all we assume that the source is having memory as far as the character set is concerned, then information theory is much more complicated. You understand whatever I am telling? If at all we assume that 26 alphabets in English language are statistically dependent, then the problem occurs is we have to define this dependency for all the 26 alphabets with each other. Same way, if at all we assume that digit 0 till digit 9, if they are related, then we have to define relationship between 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Again from 1 to 0, 1 to 2, 1 to 3, 1 to 4 like that. It becomes again 10 to the power of 10 relationships. How do we handle that? And it is not necessary also as such. Whenever that statistical dependency comes, whenever that memory comes, we will deal with it in a different way. That we are going to anyhow deal with it in module 2 and module 3 in this course itself. For the time being, let us have a simple definition that all the symbols are independent and the source is memoryless. In such a case, we can simply bring this N outside the summation symbol. And our life becomes simpler now because we can easily calculate the total amount of information which is present in a message. Hence, the average information per symbol is given by what we can do now. We have totally n number of symbols and we have m character set, and we know the probability of each symbol. Now we can find out what may be the average information per symbol. Means we know the probability of A, we know the probability of B, up to Z we know it, and we know that from A to Z there are 26 alphabets. Now we want to find out the average information for all these 26 alphabets. Something divided by 26 when we get average information. So that way we can find out the average information per symbol, that is I total by n. This n will come here. I total by n, that is summation of I equals 1, I equals m, pi into lg of 1 over pi bits per symbol. You remember this? I had discussed this earlier also. It is bits per symbol because number of symbols is n here. That n went this side. So naturally it is bits per symbol. This is called as average self-information, or this is called as source entropy, which is utilized to predict the information rate from the given source. This becomes useful for us in measuring information now in future, because our primary goal is to measure information. Only when we measure information, we can find out the way in which it is transmitted and received. So this concept called source entropy becomes important. It is nothing but average self-information, or it is nothing but the average information per symbol. Okay, this is utilized to predict the information from the given source. So now entropy is defined as H equals summation of I equals 1 to m pi into lg of 1 over pi, where lg of 1 over pi itself is self-information. And when we combine it with all the number of symbols that are present, then that becomes average self-information for the whole character set. That is called entropy, and the symbol given is H. Now what is this entropy? Entropy represents the average uncertainty of the source, and hence it is also called as average self-information. It is the average uncertainty because uncertainty itself is information here. Anything that is certain is not information. It is used to obtain the average number of bits per symbol in long messages. Let me admit the people who are waiting in lobby. It is used to obtain the average number of bits per symbol in long messages. We have assumed here that our message is long enough so that we can bring that capital N to the other side of the summation, and we can divide that I total divided by n. So naturally we should have lengthier information. For example, if your textbook is bigger or thicker, then there is an equal probability that all the alphabets which are present in the English language are present in the textbook. If anything is there with only 1 page or 2 page, we cannot guarantee that. Which means we are assuming here that our information content is much larger, and hence that capital N can be always brought to the outside of the summation symbol. So in such a case, it is used to obtain the average number of bits per symbol in long messages, and the average information rate is given by capital R equals RS into H, where RS is the symbol rate. This we had discussed earlier. The symbol rate we had discussed earlier. Bits per symbol, symbols per second. That becomes bits per second. That is what is RS. Now this RS we know because we know about the nature of the information source. And H also we will know because we know the character set which is utilized by the information source. Now the symbol rate we know. For example, if you are typing some report in the laptop, you will know your typing speed, average typing speed. Then when you are typing through the English alphabets, you will know the probability of each alphabet. Okay. When you know the probability of each alphabet from A to Z, you can easily find out H. That is this entropy. And you know your typing speed. So naturally, this capital R is the average information rate which is being transmitted when you type out the messages in the laptop into the computer's memory. In other words, if I have to tell you, if I have to give the example of WhatsApp itself, you will know your typing speed. Oh yes, our students are experts in typing through both the hands. I had seen my son typing WhatsApp message in the mobile where he will keep the mobile in between the two palms and only using the two thumbs he keeps on typing messages. I wonder at his ability. I wonder at the abilities of the younger generation people. I belong to the older generation. I have never tried such type of typing. What I do is I keep the mobile phone in my left palm and using my right palm, using the forefinger, I keep on typing different alphabets. Whereas my son is doubly or triply faster than me. Through both the thumbs, he keeps on typing messages. So, if you keep typing WhatsApp messages, then you know your typing speed, that is RS. Then the English alphabet which you are using, let us presume that you know the probability of each alphabet that is occurring out of the 26 alphabets. And let us presume that you have found out the average self-information or average information content per symbol out of the English language. They have done it already. People have already done it for the character A, the character B, the character C, like that. They have gone. I have already given you enough examples. So, H is known to us. RS is known to us. Naturally, this capital R is known to us. We can find it out. Now, based on your typing speed, based on the average information content, we can find out what is the average information rate that is going out through your WhatsApp message in terms of bits per second. Okay. Now, that is going to help us. If we can reduce the bits per second and if we can increase the information content, we have achieved our goal. For example, it is the same free space medium which is used by every mobile phone user now. Now, if we can reduce the bits per second and if we can actually increase the information content, then what it means is at any given point of time, even if many people keep on sending messages, the channel can easily transmit it. When channel gets blocked, many times you can see in the peak hours when you try to make mobile phone calls, you will get messages as if network is busy or the message comes as if it is unable to connect right now. The reason is all the communication resources are occupied for some other information transmission. That again depends on the number of bits which are being transmitted. Actually, in the present wireless scenario, it is not even gigabits per second. It is the terabits per second which are being transmitted. Now, everyone is using online mode of education and you can simply visualize how much of data is being pumped into free space and how much of radio frequency signals are being carried or being utilized for carrying the information bits. So, now it is gigabits per second and terabits per second which is going on. Now, think about it. If we can reduce the number of bits for a given message, then naturally the same shared resource can be utilized, shared channel can be utilized for more number of users. That is the essence of information theory, and that is where information theory has achieved its objective. We are going to study about it. We have beautiful methods of finding out the channel capacity and we have beautiful methods of coding in the next modules. Provided you understand all these basics, in the next modules, we are going to work out all those things. Okay. So, remember this particular formula, capital R equals small rs into H, where capital R is the average information rate, small rs is the symbol rate, and capital H is the entropy or average self-information. I'm showing you an exercise. This exercise, I will show you the solution also. For the next exercise, keep your pen and paper ready and you only have to solve it. This first exercise I will show you. Let me take a minute for sipping water. "37 students are present in the class, but in the attendance list there will be more than 60. That is what I have seen in the morning session also. Anyway, let us see this example. A source emits the symbols A, B, C, D and E. In this particular exercise, we are assuming that the source contains only 5 symbols. Okay, imagine that way, that it contains only 5 symbols. We name these symbols as A, B, C, D and E with the symbol probabilities of 1 over 4, 1 over 8, 1 over 8, 3 over 16, 5 over 16. Respectively, as it exists that summation of I equals 1 to 5 is Pi equals 1. If you sum all these probabilities, it is definitely equal to 1, because we are assuming that the source contains only 5 alphabets. If at all we take all the 26 alphabets, our exercise becomes much bigger now. So for this example, we are considering only 5 alphabets, and A occurs with the probability of 1 over 4, B and C 1 over 8, D 3 over 16, 5, E is 5 over 16. When you total them, it will become unity. Find the entropy of the source. Okay. Now, this exercise is easy. We know the formula for entropy. The formula for entropy is what? H equals 1 over Pi into Lg of Pi. Pi into Lg of 1 over Pi. I'm sorry, I told reverse. Pi into Lg of 1 over Pi. Pi is 1/4. Lg of 1 over Pi, 1 over 1 over 4 is 4. Similarly, for the next symbol, for all the 5 symbols, you can see this way. H is 1 over 4 Lg of 4 plus 1 over 8 Lg of 8 plus 1 over 8 Lg of 8 plus 3 over 16 Lg of 16 over 3 plus 5 over 16 Lg of 16 over 5. This is now the total source entropy. So, you should have a calculator there. You should take log to the base 2 only here. Now, when we take this, we get 0.5 plus 0.375 plus 0.375 plus 0.453 plus 0.524. We are getting 2.227 bits per symbol. Now, this is the entropy of the source. Entropy is nothing but average self-information per symbol. Okay, we have considered all the 5 symbols and we have taken the average information content. So, if we know the transmission rate or the symbol rate which is emitted per second, we can find out the information rate which is transmitted through the channel. Now, this is one example which is a simple example. So, students, the next example, do it on your own now. I am showing you the example here. Exercise 4, a source emits 4 messages with the probabilities 1/2, 1/4, 1/8 and 1/8 respectively. Calculate the information content of each message and the average information content per message. The source is emitting 4 messages with this probability. When you join together, it is going to be unity. Now calculate the information content of each message. Average information content per message. Information content of each message is what? Lg of 1 over Pi. Now average information content per message is what? Summation of all that. Summation of Pi into Lg of 1 over Pi. Students, please work it out. I will give you 2 minutes time. I want somebody to put the answer in the chat box. That is a proof that you people are listening to me. Manideep is there, Chandramohan is there, Indrajit is there. Yes, there are many. So I expect that at least any one of you will find out the answer and you will put it in the chat box. This meeting is going to end in the next 5 minutes. Gaurav did it and he has given the answer 9. Let me see. Let others also give the answer. Anjali has given the answer as 1.75. Just recall this formula. H is Pi into Lg of 1 over Pi. Kuldeep has given the answer 1.75 bits per message. No, it is, if it is entropy, then it is 1.75 bits per symbol. It is not bits per message. If you use the unit as bits per message, then that becomes a self-information. Manideep has given 1.75. Okay, if so many students have given 1.75, then it must be 1.75. Let me reveal. So he has asked that in the beginning, find out the information content of each message. So I of M1 is Lg of 1 over Pi or minus of Lg of Pi. That is 1 bit. I of M2 is 2 bits. I of M3 and M4 are same. It is 3 bits. Now the average information content is H is half into 1 plus quarter into 2 plus 2 into 1 over 8 into 3. That is 0.5 plus 0.5 plus 0.75 is 1.75 bits per message. That is correct. Good that students have worked it out. Here in this case I have used this method where I find the self information. Then we already know that the total information is nothing but I of M1 plus I of M2 plus I of M3 plus I of M4. We already know that. So that is proved here. You can use this formula also. You will get the same answer. You can use this particular formula also. Summation of I equals 1 to M Pi Lg of 1 over Pi. What I did is I individually find out all these things. Then I find out the total by multiplying the number of bits. That's all. So the answer is 1.75 bits per message. Let me end this class for today. In the next class, let us work out some more exercises. Yes, Chandramohan has given the answer as 1.75. That is correct. Okay, let me end the class for today. I am going to upload this video into YouTube. Those who are absent to the class, let them go through the video. See you in the next class. I am going to post the attendance link in the Google class itself.